If you listen to the tech billionaires, the future of humanity is inevitable. They tell us that merging our brains with computers is the next logical step in our evolution, that we are just a few years away from downloading skills, expanding our memory, and becoming, essentially, superhuman. But there is a gritty biological reality that the marketing pitch leaves out. You see, Silicon Valley builds hardware, but your body? Your body is wetware, and biology does not like to be hacked. Your brain is the most protected fortress in the known universe, and when you breach that fortress, even to upgrade it, it doesn't see an enhancement, it sees an invader. Today, I'm going to break down the exact neuroscience of what happens when silicon meets soft tissue. We aren't talking about sci-fi dreams. We are talking about the foreign body response, the death zone, and the brutal biological price of trying to become a cyborg. To understand the risk, you first have to respect the barrier. Your brain is separated from the rest of your body by the blood-brain barrier. It is a biological firewall designed to keep out everything: toxins, bacteria, and even your own immune system. But a Neuralink, a Utah array, or any BCI, brain-computer interface chip, has to punch right through it. The moment a microelectrode enters the cortex, it isn't a connection. It is a stab wound. Even if the wire is thinner than a hair, it tears through capillaries and neurons on its way in. Immediate impact? Microhemorrhages. Your brain starts bleeding internally on a microscopic scale. This blood is toxic to neurons, but worse, it triggers the first responders of the brain, the microglia. Think of microglia as the brain's SWAT team. In a healthy brain, they are calm gardeners. But the moment they detect that metal probe, they transform. They become activated. They swarm the electrode, releasing inflammatory chemicals called cytokines, specifically interleukin-1 beta and TNF-alpha. These are chemical screamers. They tell the surrounding tissue, we are under attack. This isn't downloading kung fu. This is your brain mobilizing for war against the device you just paid $50,000 to install. Here is where the superhuman dream hits the biological wall. Over the next few weeks, your brain realizes it can't eat the metal chip, so it decides to quarantine it. Astrocytes, the support cells, begin to build a dense, fibrous wall of tissue around the chip. This is called the glial scar. For the device, this scar is a disaster. It acts like rubber insulation. It pushes the neurons, the very things you are trying to listen to, further and further away from the sensors. This creates what neuroscientists call the kill zone. The inflammation in this zone becomes so toxic that the neurons closest to the chip often die. The electrical signal gets weaker, the impedance goes up, the device starts to go deaf. This has happened in almost every long-term BCI trial in history. The Utah array, the standard for research, often sees signal loss after a few years because the brain successfully isolates it, and it gets worse. Your brain is soft. It has the consistency of jello or tofu. The chip is rigid. Every time your heart beats, your brain pulses. Every time you turn your head, your brain jiggles inside the skull. This causes micromotion. The chip constantly rubs against the raw wound, scraping the tissue, preventing it from ever healing. It keeps the inflammation alive forever. Chronic neuroinflammation isn't a superpower. It is a known pathway to Alzheimer's and neurodegeneration. So maybe we skip the chips. Maybe we go organic. Genetic editing. CRISPR technology promises to let us rewrite our own source code. Stronger muscles, higher IQs, no diseases. But here, the enemy isn't inflammation. It's a protein called p53. To edit a gene, CRISPR has to break your DNA double helix. It snaps the strand in half so it can paste a new code. But your cells hate this. A broken DNA strand usually looks like cancer. When a cell detects this break, it activates p53, the guardian of the genome. p53 has one job: stop the cell from dividing or kill it entirely to prevent tumors. Here is the gritty irony. For gene editing to work, the cell must not have a strong p53 response. If p53 does its job, the edited cell dies. The only cells that survive the edit are often the ones with defective p53. By selecting for cells that accept the edit, you might be accidentally selecting for cells that have turned off their cancer protection system. You haven't created a superhuman. You've created a ticking time bomb. I'm not saying this future isn't coming. It is. But the current marketing glosses over the biology. Evolution spent millions of years building a system specifically designed to reject foreign objects and punish genetic tampering. The irony is that we already know how to upgrade the brain. We know that deep sleep flushes out neurotoxins via the glymphatic system. We know that exercise boosts BDNF, literally fertilizer for your neurons. True biohacking right now isn't about chips or gene edits. It's about optimizing the hardware you already have. Because until we solve the glial scar and the P53 problem, the only thing you're hacking is your own life expectancy. If you want to know how to actually heal your brain without a chip, watch this video on what happens when you quit sugar. It's the upgrade you can do today. Thanks for watching. Don't forget to subscribe.